All right, in these next examples, we're going to look at linear motion with constant acceleration, right? Before we were looking at constant velocity, so now we're going to look at constant acceleration. All right, so what is acceleration? It's the rate of change of velocity. So the velocity is changing at a constant rate if the acceleration is constant. Okay, so in this first example, we have a race car that accelerates from rest at a constant rate of 5 meters per second, right? 5 meters per second squared is the acceleration of this car. And it does this for 5 seconds. How far does the car travel? And how fast was it going at the end of the 5 seconds? All right, now I'm going to start with a graph of velocity versus time. Okay, like we said before, the area under the velocity graph gives you the displacement. So this is velocity versus time. And I know that I have constant acceleration. It starts from rest, so the velocity is starting at 0, and the velocity increases at a constant rate, right? Until we hit a velocity of, we're increasing at 5 meters per second for 5 seconds, right? So what does that mean? This is 5 seconds. So at the end of 5 seconds, if our velocity increased by 5 seconds or 5 meters per second every second, then at the end of 5 seconds we're going to be going 25 meters per second. Okay, this is seconds down here. And that's what the graph of the velocity would look like, right? Essentially, we could write an equation for this. Velocity is equal to 5t, right? The acceleration is the rate at which the velocity is changing, and so we're just taking the rate times the time, and what we're going to get in this case is velocity. So now we want to find how far does the car travel in this time period, and how fast was it going at the end of the 5 seconds? Well, we just figured out how fast it was going at the end of 5 seconds, because if it it was increasing by 5 meters per second, velocity was increasing by 5 meters per second every second, then we're going to be at 25 meters per second. So the final velocity, I'll say velocity after 5 seconds is 25 meters per second. Okay. All right. Now let's try and answer the other one. The other question is, how far does the car travel in that time period? All right. Now, the same thing holds. The distance is the area under the velocity curve, between the velocity curve and this horizontal axis. Notice that the shape is not a rectangle, it is a triangle. It's a triangle. And we know that the area of a triangle, let's write it down here, area of a triangle, right? We should know that from high school geometry, right? The area of a triangle is 1/2 base times height, right? Now, the base of this triangle is 5 units long, 5 seconds long, right? The base is 5, and we know that the height, this height here, let me just draw a little, actually. Let's do this. All right, so the height is 25 of this triangle. It's a right triangle too, because I dropped an altitude, right? I just dropped this dashed line is perpendicular to the horizontal axis, right? Because I dropped the vertical line down to the axis. And so our displacement, right? This displacement, I'll write it here. Displacement at the end of 5 seconds is just going to be 1/2 times 5 times 25. It's just the area of a triangle now. All right, when we have constant velocity, we end up with either triangles or trapezoids. All right, so our displacement is, if I multiply that out, I get 62.5. and oops, the point 5, and the units are meters, right? Because the velocity or the acceleration was in meters per second squared, so that gives us a velocity in meters per second, and then the displacement will be in meters. So that's how far we went in 5 seconds. It's 62.5. All right, so that's so again, we're just finding area. We're finding the area between the graph of the velocity and the horizontal axis, the time axis, right? And we can find the distance. So we went, or in this case, the displacement. It's the distance we traveled from the start, from whatever our starting point was. All right, so let's take a little bit of a deeper dive in this one. Okay, now I'm going to just make a little table of, we're going to go for 5 seconds. The acceleration is constant, right? So it's a constant 5. So I'm just going to fill out this table. I'm going to write out the acceleration and the velocity for this 5 second interval. All right. Now the velocity, we started at 0, right? We're accelerating at 5 meters per second every second. So after the first second, we'll be going 5 meters per second. Okay, we go for 1 more second. Now we're going to increase our speed, will have increased to 10, right? Because again, we're just increasing by 5 meters per second every second. So I'm just going to add 5 to for every second. I'm going to add 5 to the velocity. 20 and 25. All right. Now, let me actually see if I can, let's see, can I get my graphs on here? I think I'm going to make this a little bit smaller so I can see my graphs at the same time. Okay. Oops. Okay, so I'm going to see my graphs at the same time. Okay, so what I'm going to do, I'm just going to graph the acceleration as just a constant 5, right? So I'm just going to draw a constant horizontal line. That's the graph of my acceleration. Kind of boring. Now, the velocity, right, is just increasing by 5 meters per second every second. So I'm just going to get a straight line, something like that. Okay, that's a graph of the velocity versus time, right? Constant slope because it's constant velocity. Now, what about the distance? What's happening with the distance here? This is the interesting part. All right, so notice I'm just going to be finding these areas, right? The velocity is acceleration times time. And if I look at, if I look at the areas here, like if I look at the first second, right, that's just a triangle. I'm just finding the area of this triangle. And so I can, now at 0, I'm sitting at 0, right? I'm going to assume that that's I'm measuring the distance from my starting point. So I'm just going to make the displacement 0 at t equals 0. After 5 seconds, though, the distance I've traveled is just the area of that triangle, right? It's just going to be 1/2 times 1 times 5, right? That's the 1/2 base times height of that little triangle. So that's going to be 2.5 meters is how far I went in the first second. And I could just keep doing that, looking at triangles, just looking at the next triangle here. I could take the area I had before and add on the additional area, which is a trapezoid, but I might as well, it's easy enough just to see this whole thing as a triangle, right? From 0 to 2, right, I have a triangle that's 1/2 times 2 times 10, right? And so the distance I've gone now is 10. Okay, and I'm just going to keep doing that. I'm just going to draw triangles at 3. It looks like my base would be 3 and the height of the triangle would be 15. Okay, so the distance will be 22.5 meters. And then 1/2, now that 4 seconds, right? The base is 4 and the height is 20. So 80, half of 80 is 40. Now I'm at 40 meters. And then finally here after 5 seconds, 1/2, the base is 5, This is just the same as what we had before, right? This is, the height is 25, and so we're at 62.5. Okay, so notice that the distance is not increasing linearly, is it? So let's graph this distance. All right. So 1, we're at 2.5, so maybe about there. And then at 2, we're at 10. Okay, and then 22.5 is about there. And then 4, we're at 40. And then at 5, we're at 62.5, which is a little bit off the graph, so it's about here. Okay. All right, now what happens if I connect that up? Now 0, we're at 0. So let's connect this up. Let me see if I can draw a decently smooth curve here. All right, well, it's always the hazards of trying to do this on camera. Okay, now what you should notice is this is not a linear function, and in fact, it looks a little parabolic. It should look a little parabolic, right? It should look a little bit, it should be a nice smooth curve, right? So, I don't know. You get the idea, right? If I draw this, it should be a nice smooth curve. Okay, and it's parabolic. It is parabolic. So that's interesting that that we get this parabolic curve, right? So there we go. So now what we've done is we started with acceleration and we worked backwards to velocity and then all the way to distance. All the way to distance. So we've started with the second derivative, essentially. Worked our way from the first derivative and all the way back to the displacement function. All right. Well, okay, that was kind of a long example, but we'll do some more of this in the remaining examples. We're gonna use geometry to solve to solve the problems. So I'll see you in the next video.